Here we are, day 8, lecture number 13. How's the sound in the back? Can you hear okay? Cool. I tried to hide these subtitles, but it didn't work. Let me try again. Hide. There. Okay. Announcements. Homework 4 is due tomorrow. You can finish it tonight for bonus points. Project 1 is out. Hopefully you've taken a look. There's a checkpoint due on Friday. Homework 2 and Lab 3 regrades are due on Gradescope by tonight. And we've been accumulating material that's useful for you. Mostly you should have seen these if you've been going to lab. Now there's a whole Google Drive folder that you can check out with lab worksheets and other things like that. It's a good idea to review what you're working on. Maybe even before you try the homework in the project, that way the homework and the project go more smoothly. All right, so we're about to transition. We've done all kinds of things with tables, and we've looked at all kinds of visualizations. Now we're going to start working on questions like, when two numbers are different, like the average number of hours per sleep for someone who sleeps on their left side or their right side, are they different enough that it matters? Are they so similar that it might have just been kind of random chance of who you happen to ask? Or is there a real underlying difference? Working up to those kinds of questions takes a little while. But an important part of working up to those questions is to be able to think about what would happen in the world if, in fact, things were just sort of happening randomly by flips of a coin or rolls of the dice. So today isn't really going to go into these like deep questions about whether in a data set there's an interesting difference or not. Instead, we're going to build a foundation for that by asking things like, what would happen if I roll the die 1,000 times? And if you're wondering, who cares what happens if you roll a die 1,000 times? Well, I care. You will care too, because thinking about random events allows you to answer questions about the real world of the form, is this thing that I observed in the real world kind of like a random event, or kind of like an interesting real association going on there? So that's why we learn about random events, like simple things like flipping coins and rolling dice. I almost said flipping dice. I don't know what that is, but gotta have that foundation and gotta be able to do it in code so that the computer can do the hard work of telling you what it would be like if things were random. Okay, so that's where we're headed. In order to do that, we need a few more programming concepts. One is the ability to make comparisons. We've done a tiny bit of this already in the course, but I'd like to go over it in detail. You know about assignment statements. This is not asking whether x is equal to 2, it's making x equal to 2. It's assigning to the name x some value. Whereas all these expressions down here are just asking questions about what an x and y already are. So if I write x greater than y, it doesn't make x greater than y, it just checks to see if x is greater than y or not. This is how you write greater than or equal to in Python. This is how you write, is x equal to y? If there were only one equal sign, it would change x. This doesn't change x or change y, it just compares them. So that's why these are called comparison expressions. This is how you write not equal to. So this whole expression here, x not equal to 2, is only true if x isn't 2. Oh, and here's a complicated one. This says x is both bigger than 2 and smaller than 5. These are all valid Python expressions that will only give you an answer if x and y are already bound to something. Once you've made a comparison, you get either a true or a false value. If I say x equals 2, and then I say x is greater than 3, it will tell me false. If I say x is greater than 1, it will tell me true. And what about that tricky one? That was like 1 is less than x is less than 3. Well, that's true because it's between 1 and 3. This value true is also something you could type in. So you've typed in a few times, like descending equals true. Has to be capitalized. That's just a Python thing. Once you have these values that represent whether something is true or false, it is possible to aggregate them. And adding them up actually just tells you how many were true. So just like 1 plus 0 plus 1 is 2, true plus false plus true is 2. What a weird thing. What does it mean to add true and false together? Well, it just is a convenience. It turns out that there are lots and lots of times when you have a whole array of trues and falses, and you want to know how many of them were true. Well, it turns out you can just sum them up. So this is a fact that's built into Python, which is that true is just kind of another name for 1, and false is another name for 0, which makes it convenient to do arithmetic on true and false, and you can interpret the result. So that means you could sum 1, 0, and 1, and you could sum true, false, and true, and you get 2 out of it. Okay, here's why this is useful. Let's say you have an array. John, and occasionally my evil twin Jack shows up. This says for each element, oh, I didn't execute it. Like that. Okay. Start with that. We're in business. Then do that. There's an array. This says, it's kind of like doing arithmetic on the array. This says for each element in the array, is it equal to John? Well, for the first 2 it was, the second one it wasn't, and the third one it was. Or the fourth one it was. How many of them were John? Can be answered just by summing this array, which is the result of comparing this array to this value John. It says there are 3 Johns, and how many were not John? This John. So we've gone from comparisons of just one value at a time to now comparing all the values in an array to a particular value. And then what do we do with this array of what are called bool values? Well, you can sum them up. Or you could look at a particular one. All right, since this is just an array. It says assign the name A to the result of checking whether each element in S is equal to John. Okay, so now A is a bunch of trues and falses. I could get particular items in there, or I could try to aggregate them, sum them up. Just like a number has a type, true has a type. And the type is called a bool. And what is bool? It's short for Boolean. And why Boolean? Well, it's named after some logician named George Boole. So, except for George Boole had an E at the end of his name. Somehow that got lost in the passage of time. Okay, questions? Oh, I see no question. Can we use these comparisons directly in a table column? Yes, you certainly could. So if you had let's get ourselves a table. There's one. How many of the 1,343 responses said their number of piercings was greater than 0? Well, one way you could do that, you already know, which is to use where things are above 0, and then look at the number of rows. So this is something you already knew how to do. But another way to achieve the same thing would be to take the piercings column, compare each of those numbers to 0. Now I have a bunch of falses and trues. I could sum that up, get the same result. Problem with answering one question is people ask more questions. Okay. What's that sum line again? Well, there it was. Okay. What's the difference between equals, equals, and equals? This is fundamental. Okay, so my dog is named Maple Syrup. Not named by me, named by my child. Okay. If I just type in maple syrup, I get an error. If I say this is equal to 3, I will get an error, the same error, which says maple syrup is not defined. Whenever you use equals, equals, everything on the left and the right has to be defined already because you're comparing something that already exists to something else that already exists. On the other hand, a single equals changes the value of maple syrup. He was bad. Okay. This did not give me an error, even though this didn't exist before. Now it exists. Now I can check and see if she's a good dog. Oh, not so much. Okay. No cookie for Maple. Hopefully that clarified things a little bit. Totally different purposes. Single equals, change something. Assign a name to a value. Double equals, check something. Is this expression equal to this expression? As a result, you can put something complicated on the left of double equals. You couldn't do that on the left of a single equals. On the left of a single equals, it's just an error. Okay, great questions. Nothing in the room. Yeah. Oh, that's a cool idea. So if you had two functions which happen to be the same, like f of x is x plus 1, and def g of x is something really tricky, like x minus 1 plus 2 or something like that. Could you say, hey, is f of something equal to g of something? Is this what you're asking? It doesn't do that. It's not going to like go through and inspect your function and tell you whether it's true. It will tell you it's true in this case because x happened to already be defined. If I used something that was just a placeholder, I'd get a name error. It really only compares numbers to numbers. And if you ask, is f equal to g, it's not smart enough to check and see if it's true for every possible value. It just checks to see if they're the same function or not. So you'd have to go through and pick a bunch of different values, like and check them yourself. Like, is it the same for 1, and is it the same for 2, and is it for the same for 3? And if you decided all those were true, maybe you thought they were the same function. Remember that the stuff that's kind of built into Python is all just like basic building blocks. You could then build something that checked whether two functions were equal through some more elaborate process, but you'd have to write that yourself. Okay. Here's some other fact. A row of a table. What is that? A row is something you can access with the row method. I'm not sure if you ever did this before, but you can do it. Just pick which row you want. What you get, a row, is kind of like a list. It's got items in it, and you can sum it up. Now, sum is only going to work if it happens to be that all the values in the row are the same kind of thing. They're all numbers. You can get an item even if it's a mixture of numbers and strings. So yeah, here's some survey. Here's what a row looks like. It's got all the data in there. Row 0 is the row at index 0, has second, 5, 5, 8, etc. And I could get a particular value out of a row, just like I could get a particular value out of a column. I could get the second out of there because it comes first, index 0. I could get the hours of sleep out there, index 3. One thing that's special about rows, which means they're not exactly lists, instead they're rows, is that you can access the items by the labels that showed up in the table originally. If you really wanted to be explicit about what's going on, you could take this row and get the hours of sleep that way. But another thing that's cool about a row is if it's just full of numbers, which happens on occasion. Like for example, if I took my survey and I selected just columns 1, 2, and 3, and then I grabbed a row of that. Instead of show, we get a row. How about row 1? We'll call that R1. This has 2, 3, and 7 in it. Okay, so if we sum it, we'll get 12. And occasionally this can be useful. Like if we wanted to pivot to get counts of 0, 1, 2, 3. How about handedness and pant leg? Now I have a row that's almost all numbers. So, what if I wanted both left-handed, right-handed, and the total? How would I get the total? Well, you could do it with a group, or you could do it just by summing across the rows of this table. So I could take this, give it a name, the pivot, and then I could add another column of the total, which is the result of taking the pivot, drop the pant leg column. Now I just have the numbers. Oh, I got a little bit ahead of myself. Let's not with column. Let's just look at this thing. Drop the pant leg column, and then pick a row. Like row 1, and then I could sum that up. And now I have the sum of 7, 42, and 414 just by kind of working with the table that I already have. That's like a convenient thing you can do with a row. Most of the time, you need to work with a column. Every once in a while, you need to work with a row. Now you know how to do it. Questions? Trying to make it sound simpler than it is. I know that there's a lot to learn, but you're getting there, I can tell. Yeah, a row is more like a list or a column. So once you have a row, you can sum it up, you get a particular item, just like a column. And then the table itself, things like where and pivot, they won't work on a row, they'll only work on the whole table, because you need like rows and columns to do those kinds of things. Great question. Oh, these are just the indices of the pant leg and handedness columns. So I could have written them out and it would have worked just as well. Probably better to write them out. Then you really know what they are. Oh, except I can't copy and paste very well. Okay, I think you get the idea. Question. Oh, so the question is, what if we wanted a whole column of totals? Let's do that next. Thanks for setting me up. The easiest way to do that, assuming I can here, is to use apply with the sum function. Apply, remember, takes all the values in some column and applies some function to each one. Well, you can also use apply to apply some function to each whole row. So before, you're used to seeing apply f, and then we had to name the column that had the arguments to f, that had all the inputs to f. But if I just write t.apply to f, then what it's going to do is apply f to the whole row for each row in the table. So t.apply f for a table t and a function f creates an array of the results of applying f to each row of t. This only works if f is the kind of function that can take a row as its input, like sum, for example. So if I write t.apply sum, what it's going to do is sum across each row and give me an array of the sums for each row. Get rid of that. Oh, I don't like you. I want you to hide. Thank you. We got this one number, 643, but instead we could have said p.apply the sum function. We're going to get an error because you can't sum 110, 185 and the string I don't know. You'd have to first get rid of the pant leg column. Similarly, we could have written get rid of pant leg. And then we apply sum. What did that do? It actually did a lot of work. It summed these three numbers together, then these three numbers together, then these three numbers together, and gave me the results of all three. I got 196 and 643 and 684, which means if I wanted to add a total column, I would have all these things ready to go. Boom, 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 196. So every once in a while, the lesson here is every once in a while, what you need to do when you're applying a function is not taking the values in a particular column or two columns, but you want to take in the whole row, however long it is, and do something with it, like sum it up. Now you know how. Okay. So we learned something cool we could do with a function. Oh, let me just read these for a second. Let's see. Well, we answered that. Amazing. I love it. What did survey.labels do? It gave me all the labels in the table, which are the names of the columns. There was a question in here which was like, when you get a row, is it really an array? That's not quite what you asked, but it's pretty close. Let's take a look at this thing. It's not an array, it's a row. Because an array looks like something else. 141, 642. That looks like an array. And this looks like a row. It turns out you can sum either one, so that much is easy. But there's some things you can do with this array, like add 12, that you can't do with this row. You ever run into that kind of situation? You can say, look, this thing, this row, it looks so much like an array, I want it to be an array. Well, it turns out there's a NumPy function for that. This is not something I think you need to use at any point in this course, but now you know. It's pretty common that if you want to take something and turn it into a string, then you call stir on it, and if you want to take something and turn it into an array, then you call np.array on it. If it can't figure out how to turn it into an array, it's going to give you an error. But if we can figure it out, which is basically like this looked like an array in the first place, just the right kind of thing. Now we can turn it into an array. Hopefully that answered your question. And what if you wanted to drop a row? What would you use? I believe it is called exclude. Let's see if I'm right. I'm testing my knowledge of tables. P. It's going to work. Exclude row at index 2. Let's go. It's kind of like drop. Drop drops a column, exclude excludes a row. How can you tell? You just have to memorize it. All right. Good questions online. Good questions here. What do we got next? More stuff? Question. Great question. So how's the apply today different from the apply we already learned? Let's take a look at our survey table. Before I showed you that if you wanted to do something with each value in here, like then I would apply some function to the extroversion column. This we did before. And what's this function? Well, it takes in the value, which is like some number, and let's say we want to check and see if it's greater than 3. Get your return. Then it would give you back an array of the results of applying this function f to every value just in the extroversion column. This kind of apply we did here. Scroll, 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 confused, 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 confused. Where'd it go? I lost it. Oh my God. Oh, there it is. This kind of apply here didn't, yeah, let me just paste it down. We could have written our own function. But f wouldn't have been good because f just takes in a single number. We would have wanted to take in something that takes in a whole row of numbers. And what would it do with that row of numbers? I don't know, check whether the sum of the row is greater than 3. So the contrast is, this took 2 arguments, what function and what column of values to apply it to. This just took 1 argument, what function, and applied it to all the rows of this. Here we needed a function that took a number. Here we need a function that takes a whole row. It's doing the same thing. It's just applying the function to each row, except for like whether it's doing the whole row or just a number within. Oh, good questions. Okay, let's keep going. We're gonna do a little more programming. If you could see the slide, that would probably be better. There's things called control statements, which control the sequence of computations that are performed in a program. So like up until now, I think we've basically just been doing things from top to bottom. Like you can put multiple lines in a cell, it'll execute the first line, execute the next line, execute the next line, kind of build stuff up that way. Control is about making it so that some lines actually get executed twice and some get skipped entirely. That's what it means to control the flow of execution in a program. We'll use 2 kinds of control statements. We'll learn about them both right now, if and for. The purpose of if is to define functions that choose different behavior based on the argument that comes into the function. So let's take a look at some examples. If x is 20 and s is a string, you are 20, I can write an if statement. It's actually a 2-line statement where I write if and then I write some condition, which comes out as true or false. And then if it's true, this happens. And if it's false, it doesn't happen. So is x greater than or equal to 18? You bet it is. So now S is changed. Is x greater than or equal to 21? It's not. So S never got updated. Even though we had this line of code in our program, it didn't run. Because it's part of an if statement. And this part of the if statement that's indented only runs if this is true. This person didn't quite make it. And so people who are not 21 never drink, as far as I know. Okay, so when you turn 25, you execute the same statement, you get different behavior. Now, since this expression is true because we changed what x was, we get a different result for s. It's pretty unusual that you'll see an if that's not part of a function. What is more common is that you'll see a function, like the age function here, which has if statements within it, because you don't know what x is, so you're going to find out. I could call age on 3, and this wouldn't be true, and this wouldn't be true. So what would happen? I get nothing. If age were 20, then this is true, this is not true, so I get you can legally vote. If age is 25, then I get that this is true, and this is true, so, you didn't get to drink. I'm going to tell you why. While this is something you're allowed to write in Python, it doesn't do what you want it to do. Because the way Python works is that when you call this function, it goes through all these if statements from top to bottom. It checked to see if x was greater than or equal to 18. It was for 25. And so it returned, you can legally vote. When you return from a function, you're done. Nothing else happens. Key point. People often forget this, but it's an important one. As soon as you return from a function, you're done. Nothing else happens in that function. So that means it never even got here to check whether, to check your ID at the door, okay? You have to be careful about how you write your functions so that the right behavior occurs. So there's a little bit more I'll tell you about if statements that lets you control for this kind of thing. Here's a better version of the same function. Okay. X. If x is greater than or equal to 21, which is the first thing I want to check, then it says you can legally vote and you can drink, because we kind of took into account in our minds that it could be that you're both over 18 and you're over 21, and we handled that case. What this says is only check this if the stuff above it in the if statement wasn't true. So elif stands for else if, and this only gets checked if the if condition was false. So if it turns out that x is 20 and therefore this is false, then it's going to check and see whether x is greater than or equal to 18, which it might be, and then it would return you can legally vote. This only runs if all the if elif conditions were false. Like you're only 3 years old. You don't like my joke? I like my joke. Okay. This function doesn't have any weird behavior. I think I can pass in any number and I get a reasonable response. I did have to think a little bit about how to construct it. And the thing I thought about was think in my mind, what are all the x's that could possibly be? And then if I run through these conditions from top to bottom, do I always get the right result? So for any x bigger than or equal to 21, I get something reasonable. For anything that's not bigger than 21, but is bigger than or equal to 18, I get something reasonable. And if neither of those are true, then I get something reasonable. Okay, so that's kind of how you have to think about constructing a function that contains multiple different conditions that you want to check. Question in the back. Good question. So do I always have to return or can I print? Depends what my function is for. I've used F a few times, huh? Let's go with H. What's the difference between return to plus X and print 2 plus X? They look the same, but they're in fact different. I'm going to tell you why they're different. If you want to do something with the result, like then add another one to it, you need to return. And so this is why we pretty much always return. Is that the return value is something that you can then continue to work with. Okay, yeah, so good question. If this were an if instead, would it still work? And will we have to change it somewhere? Like you suggested, maybe this is 18 is greater than or equal to X. Oh, I did this wrong. 21 is greater than or equal to X is greater than X is greater than or equal to 18. Yeah, that would work too. I mean, what Python does under the hood is slightly different because it's making these slightly different comparisons, but the behavior of the function is going to be the same because it happens to be that, yeah, you kind of express the same thing in two different ways. Question? Wrong class for that, but great questions. If you want to come up afterwards, we can check. Okay, so the question is, what if you want to return two things instead of one thing? You can do it, because Python's very flexible. We never do it in this class, because usually the answer is, write two different functions and call them both. So there are special occasions where you want to return two things. I'll give you something that is within the scope of this class that you could do, is you could take those two things, put them into a list with square brackets, and then return that list. And then you kind of return both things, just all bundled up into one. The question is, if you apply a function to a column. Oh, this one. Yeah, let's try that out. Table with column ages 3, 20, and 25. Apply the age function to the ages column, you get all these different messages. Yeah, so all these things can kind of be pieced together. Well, good questions today. Okay, onward. I'm going to teach you how to randomly select something, which is with a built-in np.random.choice, which selects uniformly at random, which means that each option in an array has equal chance of being selected with replacement from an array. What this means is that if you make a random choice multiple times, you might get the same item of the array multiple times. Selecting it the first time doesn't change the chance that you'll get it the second time. You might just get it the second time too. And you get to specify a number of times. So I can say np.random.choice, an array that contains heads or tails, and a sample size like 12, and then it's going to give me either heads or tails 12 times with equal probability for either choice. Okay. Get that demo. So let's play a game. We each roll a die. This is not the most fun game. This is like something that a stat professor would come up with, but here we go. If my number is bigger, you pay me $1. I like that part. If they're the same, we do nothing. If your number is bigger, I should delete this part. No, okay, we'll make it fair. So I pay you $1. Find a way to simulate 2 dice rolls and compute how much money we win or lose based on the result. And then we're going to do this 10,000 times and see what happens. This is like asking a computer, please pretend that something complicated but random happens in the world and tell me how it came out. So we got to use an if statement to do this. We're going to first work on what happens if just I roll a die, you roll a die. So that's 1 round of this game. And then we might play again. So the function just does 1 round by checking the value of my roll, the value of your roll. And if my roll is bigger than your roll, then I get $1. Hooray. And if your roll is bigger than my roll, well, we haven't really handled that case yet. We need to do some more work. So it looks something like my roll is equal to your roll, 0. Otherwise, it must be the case that my roll is smaller than your roll. That's the only possibility. So, -1. Now we can play the game if I already know how the dice come out. If mine's bigger, I win. If yours is bigger, you win. How'd you get -1? There's no 7, and there's no -1. So this works even if we get like crazy dice. But the point is, I'm going to try not to cheat too much. And if your roll turns out bigger than my roll, then I'll lose $1, meaning you get $1. Oh, I deleted that because I didn't want to lose $1, I think. Okay, so here's the random selection function. If I call it with just an array, it's going to give me 1 outcome. So my alarm goes off, I sleep in. Alarm goes off, I sleep in. Alarm goes off again, I wake up. Notice that no matter how many times I run it, I still have a chance to sleep in. Excellent. But if I call np.random.choice with an array of possible outcomes and a number, then I will get an array back of the result of randomly choosing one of the 2 elements of the array over and over again with replacement uniformly. Uniformly means they both have equal chance. With replacement means I can get the same thing twice. Here I've done a combination. What does it mean to check the sum of the results of whether this array equals wake up? Check in with the person next to you. What does this expression do? 60 seconds, go. Trying to answer what that does. I want to highlight it. Oh, nothing in the Q&A. Nobody asked, what does this do? Maybe because you're telling each other. This randomly chooses 7 times between sleep in or wake up. This gives you back an array of 7 trues and falses for each position in the original array. Is it wake up or is it sleep in? And sum tells you how many were wake up. So I tried 6 times whether to decide whether wake up or sleep in, equal probability either way. And okay, so 6 were wake up. So 1 is, uh-oh. What happened here? Just trying to make sure you're paying attention. What happened here? That every time I run this, I'm making new random choices. So I'm not going to get the same thing every time. And likewise, every time I run this, I'm not going to get the same thing. I am running 7 different little sleep in, wake up experiments, but I'm running them fresh every time I execute the cell. If, by the way, you did want them to sum to 7, you could run the simulation 7 times, store the result, and then perform computations on this result. These 2 expressions are guaranteed to sum to 7. If I ran this again, I might get different sums, but they would come up to 7 in total. So just be aware, every time you execute this expression, np.random.choice, you're going to get new random choices. Question? Oh, great question. So how is it doing random things? I didn't see any dice flip in my computer. There's like a whole field of computing about how to simulate random numbers. It's pretty involved. Tends to have to just like, well, basically like you can find a source of randomness in the world, like how hot your computer is, and use that. Or you could just use math, and then it's not really random at all, but it looks kind of random, called a pseudo-random number. And by default, that's what Python does. So just kind of go with it, but it's not quite random, but it will be different every time. And if you do a bunch of analysis on it, as far as you can tell, it will look like a random number. Okay, we wanted to play our fun game. So here's the faces of a die. Includes the 1, excludes the 7. If I roll a die, it looks like that. To play our game, I'm going to roll a die. I'm going to roll a die for you, and then I'm going to call the 1 round function, which tells you whether or not I made $1 or I lost $1. I won. Hello. Okay, nobody paid up. Okay, that means I don't have to pay anybody. To finish this simulation, I'm going to have to teach you a couple more things. They're pretty quick. One is that, go away, Zoom. If I have an array and I want a longer array with all the values in this array with 1 more value at the end, then I use something called np.append. Value has to be a number for an array of numbers or a string for an array of strings. The same kind of thing that can go in the array. I can also use this if I have an array of numbers and another array of numbers to make 1 long array with all the numbers from array 1 and all the numbers from array 2. You'll play with this in lab, so I'm not going to dwell on it. But I will show you that if you have 1, 2, 3, 0, 1, 2, 3, and you want to add a 6 on the end, you do it like that. And if you have 0, 1, 2, 3, and you want to add 10, 11, 12, 13, 14, 15, 16 on the end, you do it like that. Hopefully that wasn't so fast that I totally lost everybody. But I wanted to get to the interesting part, which is to play our game together. Here's how we can do it. I wrote a function to play 1 round of you roll a die, I roll a die. I now have empty results, but I could play the game once, and then I could put that result on the end of results. And then if I do it again, I get more results. If this doesn't make sense to you yet, you'll just practice in lab and it'll make perfect sense. It's very common that what you want to do is do 1 random thing and keep track of it by appending it onto your list of results. We'll do this over and over in the course. So eventually you'll master that. And the last part of playing the game, I'll go over this on Friday, but I'll just show you. There's another structure, another control statement that says do something 5 times. So instead of me having to sit here and execute it over and over again, I can just say, please, Python, make it happen 5 times, and it will happen 5 times. Or I could do it 50 times. I promise I'll explain the code on Friday, but I just wanted to show you that if you play it 10,000 times, then you could make a table and draw a bar chart, and you could see that we wasted a lot of time because we ended up basically with the same score because we had the same chance either way. Okay, we'll do it in a little bit more detail on Friday. We'll see you then.